Today we will be studying module 4, that is subsystem design and FPGA based system. In this module, we give an introduction into what are the subsystems and how they are developed using the basic gates. We know that any given large system is initially broken down into subsystems, and these subsystems are designed based on the top-down approach. In the top-down approach, we start from the higher end and reach the basic level, or that is called the basic leaf cell of any digital system. The basic leaf cell of a digital system will be the logic gates. So in this module, we will study about the behavior of the MOSFET, NMOS and PMOS as a switch, and what are the basic gates using which the subsystems can be developed. Next, whenever we are designing, high regularity has to be maintained so that the design complexity gets reduced. Here, regularity means reuse of model. So, whenever possible, wherever possible, models or circuits has to be reused so that our design becomes more effective. While designing, there are certain architectural issues which has to be addressed. That is, as the complexity of the system increases, the design time and the circuit cost will also increase. So there has to be a method or algorithm which can effectively manage the complexity and make the design more effective. The guidelines which we have to follow when designing is the circuits have to be defined properly, and the partition of the circuit and we have to partition the circuit into appropriate subsystem, which can be designed or modeled correctly and efficiently. Then proper communication path has to be developed so that subsystems can interact. We have to draw the floor plan for the given design. Then we have to reuse any component, that is regularity. That is what is regularity. We have to reuse any circuit or component efficiently, which reduces the time as well as the complexity and cost. Convert each cell into layout and then start designing. Carry out design and check carefully throughout. Using design rule, we have to verify the correctness of the circuit, and finally simulate and see whether the circuit is working properly. So these steps has to be followed whenever we design a subsystems or systems. Coming to the MOSFET, which works as a switch. We know MOSFET, there are two types of MOS transistors, NMOS transistor and PMOS transistor. And NMOS transistor, it is on when gate signal is 1 and it is off when gate signal is 0. PMOS transistor is on when gate is 0 and it is off when gate is 1. So it will act as a switch. When you give gate, depending on the gate input or the control input, the transistors are either on or off, depending upon whether it is 1 or 0. So if it is 1 for NMOS, it is on. For PMOS, it will be off. Coming to the switch logic. Now, based on this NMOS or PMOS, we have pass transistors. And the switch logic, we have pass transistors and transmission gate. What a pass transistor is? This is a pass transistor is basically made of N or PMOS transistor, which connects two nodes. The signal is passed from one node to another, usually input node to an output node, with the help of a control signal, under a control signal which is given to the gate voltage. That is, when a gate voltage is given, the switch is either on or off. Depending upon what voltage is there on the input node, that will be passed to the output node. And the switch or this transistor will be in high impedance state when gate voltage is not, the control signal is 0. And pass transistors are widely used in ROM, PLAs and multiplexes. The advantage here is the geometry of this, the area required will be less, and it doesn't dissipate standby power. Whereas it has a major disadvantage that the voltage levels will degrade along with the threshold voltage. The output voltage will not be what you apply. It will get degraded depending on the threshold voltage. And you cannot drive another pass transistor using a pass transistor. A second pass transistor cannot be driven using a first transistor. Never drive a pass transistor with output of another pass transistor. These are the major disadvantage. Coming to the pass transistor, this is called the N pass transistor. What we have here is the N pass transistors. This is the N pass transistor here. This it is basically the gate is a control signal. We have source and the drain. It can be output and input. The output and input depends upon whether you're charging or discharging the node. First when you are giving input voltage, that is in this case, this N pass transistor, when the input voltage is VDD, the output voltage, the output, and when the gate input is 1, the transistor is on. Now, the current flows from, and the output we have connected a capacitor here. And when input is VDD, current starts flowing from the input and current flows towards and charges a capacitor. And we think our capacitor voltage should reach VDD. The ideal case is something like this, should reach. But it never reaches VDD. It is less than VDD. It is less than VDD by a factor VTN. The output voltage is VDD minus, it is VDD minus VTN. VDD minus VT, and it is not VDD. It is not VDD. VDD is this voltage, the input voltage. Output is always less than VDD. By what factor it is less? By minus VTN. Suppose the input voltage is 5, threshold voltage is somewhere 0.7, you get around 4.3. It is never 5 volt. Whereas if the input voltage is 0, the output, the capacitor will discharge like this with VG equal to 1. The capacitor will discharge and it will discharge completely and the voltage will go to 0. The voltage will go to 0. So we say NMOS transistor is weak passer of 1. That is, if I give a 1 here or VDD, the same 1 doesn't reach the output. It is always less than 1. Whereas if I give a 0, 0 is effectively passed. So it is a strong passer of 1 and a weak passer of 0. This is very important. It is a weak passer of 1 and strong passer of 0. See here, when the gate is 0, anyway transistor is off, and gate is 1 or VDD. This is 1 or VDD. Output voltage is 0, input is 0, output is 1. So strong passer. So output is 0 when input is 0. So strong passer of 0. Whereas when input is VDD, it is output is VDD minus VTH. It is weak passer of VDD or 1. Similarly, the next, that is here, when we are going to the next one, this is the P transistor. This will be the P transistor here. Again, we have the gate control and source and drain. When with VG equal to 0, here VG has to be 0 for PMOS to be turned on. With VG equal to 0, when Vin is equal to VDD, output is equal to VDD. The voltage across this capacitor, that is, the capacitor will fully charge to VDD. Whereas when input is 0, the output will never reach 0, but it will be a value higher than 0. A value, if it is 0 and if this value is around 1, instead of reaching 0, the output voltage will be at 1 volt. So PMOS is a weak passer of 0 and strong passer of VDD. It is opposite to what we saw in NMOS. NMOS, weak passer of 1. This is strong passer of 1. NMOS, strong passer of 0. PMOS is weak passer of 0. So this is very important. And here, if we start looking at this, the output, if I give VDD in NMOS, if I give VDD, output is not VDD. And we cannot drive another transistor or another circuit assuming this will be VDD, because our output voltage we will not get the desired output. So this is one disadvantage, that is our output voltage doesn't comply with the actual input. So to overcome this, transmission gate was developed. Transmission gate, it is a combination. Transmission gate means it is a combination of P and NMOS which are connected in parallel. The current can flow either in PMOS or an NMOS depending upon the input given. So now this is a transmission gate. This is how transmission gate looks like. It is called TG. Transmission gate is also known as TG. When we give input equal to, whenever we give input equal to 1, when input is equal to 1, which is the strong passer of 1? PMOS. So it current flows like this and output becomes 1. When we give 0, NMOS is a strong passer of 0. So current flows from VDD to NMOS. Here the capacitor discharges. Capacitor discharges through NMOS and it becomes 0. The output becomes 0. So here, depending on which input you give, either the NMOS or the PMOS transistor is here. Look, either it is depending upon, if it is 0, the PMOS, here if it is 0, NMOS transistor is on. If it is 1, the PMOS transistor. If it is 1, PMOS transistor is on. So depending on what is the input, either N or P transistor will be turned on, but output will not get degraded. Whereas in pass transistor, output is degraded. Either you use a N transistor or P transistor, output will be degraded. So to overcome that, transmission gate is used, which will give proper VDD and 0 voltage. So this is important here. For an N transistor, N pass transistor, V out is minimum voltage of V in, Vg minus Vt or Vgs minus Vt. For a P transistor, V out will be maximum of V in, Vg minus Vt. Please write this down and we'll do problems based on this. Coming to this problem here, see, calculate the output voltage when V in is equal to 2 volt. When V in is, that is V in is 2 volt and V in is 4.5 volt. There are two input voltage for which you have to find. The first case, when V in is 2 volts, this is a N pass transistor. This is an N pass transistor. N pass transistor. For an N pass transistor, this will be the circuit. So if it is an N pass transistor, and they have given Vg is 5 volt and Vt is 0.7 volt. Now Vg is 5 volt. V in the first case is 2 volt. What is the output voltage for an N pass transistor? N pass transistor will be what? The output voltage is, if you see, it is minimum of V in, Vg minus Vt. So what is now? V out is minimum of V in, Vg minus Vt. V in is 2 volt. Vg they have given is 5 volt. Vt is 0.7. So 2, 4.3. Which is minimum of these two? It is 2. So output voltage will be 2 volt. For the next case, when V in is 4.5. Again, same thing. Vg is 5. Vt is 0.7 volt. V out is minimum of V in, Vg minus Vt. V in is 4.5. Vg is 5. Vt is 0.7. So what is, it is 4.5, 4.3, which is minimum of this, it is 4.3. So now the voltage is 4.3. See here, the input voltage given was 4.5, but output voltage we get is 4.3. So it does not, lower voltage will follow, but when you are giving higher voltages, it never comes. So it is not reliable. Next case, the next problem, calculate the output voltage with Vg equal to 8.3 and Vt equal to 0.7 for different cases. Va equal to, this is equal, Va equal to Vb, which is equal to 3.3 volt. When Va is 2 volt and Vb is 2.5 volt. When VA, that is, this is a circuit given. They've said VG is 8.3. This is VG 8.3. This is not 8.8. It is not 8. It is 8.3 volt. Please write down as I'm explaining. Write it down in your note. Okay. So now this is a circuit given. Now see what is they have given. The first case VA equals, this is equals VB, which is equal to 3.3, and they have given VG is 8.3. This is 3, okay, 8.3. Then VT 0.7 is given. So what is V out? This is a NMOS, again NMOS transistor. This is NMOS transistor. This is also an NMOS transistor. V out is minimum of V in. What is the equation? What is the equation for us? It is minimum of V in, comma, Vg minus Vt. This is the equation. V out is minimum of this. So now minimum of V in is what here? For the first transistor, this is a first transistor. So for the first transistor, what is a V in? This is V in. This will be V in for the first transistor. And what is the V out? This is a V out for the first transistor. So V in is nothing but VA, VG 8.3 minus 0.7. So what is the minimum of these two values? 3.3. You give an input voltage of 3.3. For minimum value, it works. 3 point output voltage here is 3.3 volts. Then this 3.3, it is given to, this output is given to what? This VG of the second transistor. VG of the second transistor is nothing but 3.3. This is V in for the second one now. V in for the second transistor. Output V out will be V in. V in is what? VB, comma VG. VG here is what? V out is nothing but here, this is equal to V out 1. Okay, this is nothing but V out 1. So VG2 is nothing but V out 1. So that is 3.3 minus 0.7. It is 3.3 comma 2.6, which is the minimum. It is 2.6. So this is for the first case. Similarly for the second case here. Second case, please try to do this problem when VA is 2 and when VB is 2.5. What will be the this value in the when we are doing like that? Here, shall we try doing it? What will be in the first case? What is the output? Let us try here. In the second case, VA is what? VA is nothing but V out 1 will be equal to V in. V in is VA 2, comma VG will remain the same. It is 8.3 minus 0.7. 0.7. So what is the answer? This is going to be 2, comma 7.6. So now 2, comma 7.6. So it is a minimum value. This 2 is nothing but what? 2 is nothing but VG2. This is nothing but VG2. Then what is V out? V out 2 will be what? Minimum of, it is minimum of VB. VB is nothing but V into V into V into is what? VB, comma VG, with VG means what here? VG2 minus VT. What is VG2? VG2 is nothing but V out 1, isn't it? It is given there, V out 1. So this will be equal to what now? VB is they have given in the second case, it is 2.5, comma V out 1 was 2 volts, 2 minus 0.7. So now what is the answer in this case? It is equal to 2.5, comma it is 1.3. So what is the answer? Minimum of this is 1.3. So this is for the second case. Similarly, the next problem, we'll do the next problem. Find Vout voltage for this given circuit. Okay, and it is given Vg here is, in all the case it is equal to, the first here they have given Vg as VDD. Okay, V in here they have given it as VDD. V1 is nothing but Vout1, which will be minimum of Vin comma Vg minus Vt. Vin is VDD. First case, for the first transistor, Vg is also VDD minus Vt. So minimum of this will be what? It is obviously VD minus Vt. This V1 is nothing but input to the second transistor. So Vout2 will be Vin, that is output from the first one is nothing but Vin for the second one, minus Vg minus Vt. Vg is again given as Vd. So it is VDD minus Vt, comma VDD minus Vt. It is same. So it is VDD minus Vt. What is V3? V3 is the output for the third. What is the gate of the third transistor? V2. It is VDD minus Vt. This gate, output of this is given as gate input for the third one. So this is equal, this will be equal to Vg of, this will be equal to Vg3. Okay. So what is the output now? Now minimum of Vd minus Vd, Vg minus Vt. Vn, they have given it is nothing but VDD. Vg is this one, VDD minus Vt minus Vt. So VDD comma VDD minus 2Vt. This is the minimum value. Similarly, go on substituting and you'll find the final V5. V4 is again Vn minus Vg minus Vt. Here Vg will be nothing but output for this one. Output from this one is this value. So it will be Vd minus 3Vt. This is the minimum value. Again, this is given to the gate of the fifth one. So finally, what will be the output here? Final output will be, it is minimum of VDD, comma VDD, comma VDD minus 4Vt. So what is the answer now? What is the minimum of this? It is VDD minus 4Vt. This is the answer. This is the answer which you have to write. Similarly, you have another problem here. This is for, again, this is also for an N transistor. The values are given for different. We'll just discuss the first one. Remaining you have to do. Find the Vout when VDD. If VDD is equal to 3.3, VDD here is nothing but Vg. Vt is point. It is given as 0.5. Here Vt is 0.5. First case when Va is 2.9. Minimum of Vn comma Vg minus Vt. Vn is 2.9. 3.3 minus 0.5. Minimum of this is 2.8. Similarly, do it for the other cases also. Okay. Here again, they have given the problem is there. Anyway, the PPT will be shared. So please write down this. Try to do it for yourself and note down. It is the same as what we did previously for this case. For these cases, how we did. Same based on that. This problem is there. Try to solve it. Next, implementation of logic gates using the pass transistors. Okay. How to implement? Suppose we have to implement pass transistors using the logic gates. First, AND gate. Let us write the truth table. A and B are the input. Y is the output. 0, 0, 0. This is the truth table. Now, just bifurcate the input and that is the output. See here, Y is equal to A when the control signal or when the gate signal is A bar, and Y is equal to B when A is equal to A. When C is equal to A. If we can write this, that is based on this truth table. y is equal to a when c is equal to a bar. A bar here is, if a is 1, a bar will be 0. And y is equal to b. This is 0, this is also 0, 1, 1. When c is equal to a, that is when c is equal to a, here is 1 and 1, y will be equal to b. When control signal is a bar, that is when a is, that is 0, your y will be equal to a. Y is equal to a and y equal to b. When y is equal to a, when it is control signal is a bar, y is equal to b when control signal is a. The same thing can be implemented using a transmission gate. This is implementation using a transmission gate. Here, if instead of, see here, it is easy for us to write. If this is the NMOS transistor, okay, and if you have to implement a transmission gate for this, this is the NMOS transistor that we write, and this is the control signal. If you have to implement a transmission gate, a replica, a PMOS, you can just write a PMOS for this. This will be the PMOS. You have to write a bubble here. Okay, you have to put one bubble here. A small bubble has to be put. And here, if this is A, then this, that is a control signal, here is A. Then here, this becomes A bar. That is the only difference that we have. This becomes the, this is the out, this becomes the input, and this becomes the output. This is the transmission gate. See here, this is NMOS. So on the bottom they have written a PMOS. This is also an NMOS. So on the bottom they have written something like this, and they have implemented this the P transistor with the bubble. There's a bubble here, and this is A, means this becomes A bar. If this is A bar, this P transistor you have to give us A. The negation value you have to give. So this is the implementation using TG, transmission gate. Next, implement a OR gate. Again, we write the truth table. Divide this truth table into half. Look at this, y is equal to b when control signal is A bar, and y is equal to A when control signal is A. So same thing can be implemented using the pass transistor, and the negated value will be TG. If you have a doubt, please refer a call up or just give a call so that we can discuss this. Next, implementation of a NAND gate. Again, same thing. Write the truth table and divide this into half. Y is equal to A bar when control signal is A bar, and y is equal to B bar. Okay, this is 0 means this is 1, so it is y is equal to B bar when control signal is A. For that you have to write, that is first y is equal to A bar when control signal is A bar, y is equal to B bar when control signal is A. And if we can draw, that is, as I said, if we draw the inverted for this, if we draw the P transistor, and here instead of A bar control signal there will be A. For this, if I draw the P transistor, let me draw the P transistor for this. We'll have to put a bubble. Have to put a bubble here. This represents the P transistor, and here the P transistor here. See, this is a P transistor for this. The control signal was A here, so the control signal here becomes A bar. Similarly, here you have to draw, for this we have to draw P transistor, and the control signal for that P transistor becomes A, because for N it was A bar, for P it becomes A bar. Sorry, for P it becomes A. Similarly, for NOR gate, truth table, look at this, y equal to B bar when control signal is A bar. If it is 0, we have to write it as A bar. And y equal to A bar when control signal is A. You can write it as A or B, but here whichever that is, this is more convenient because it goes to either 0 0 or 1 1 here. So usually A becomes easier for us to take as a control signal. Then coming to the next one, we can implement mux. Okay, that is 2:1 mux means this is 4:1, this is 2:1. Control signal again. When S is 0, it is A. When S is 1, it is B. So S0 means it is S bar. It is A. Output will be A. When it is S1 means S, it will be B. Similarly, based on this, 4:1 transistor, sorry, 4:1 mux can also be implemented. All let a lot of things which can be lot of other logic circuits which can be implemented. So for now, you can try, that is, you can try to implement half adder, other circuits also.